Santosh, everything ready? Shall we begin? Okay. Recording started? Okay. So good morning, everyone, and welcome to this series of lectures on stellar structure and evolution. You have had a glimpse of the broad brush view of astrophysics over the last week, and also got to learn about various processes by which astrophysical objects radiate, and how we can learn things about objects by looking at their radiation. In this series of lectures, we'll go a little deeper on stars, their structure, and how the stars change their structure and appearance with time, which we call stellar evolution. So let's begin. Stars, of course, if you go out and look at the dark night sky, you will find many points of light. And basically, most of the light we see from the universe comes from stars, be it bright points of light which you see, or even diffuse batch of stars like the Milky Way. The Milky Way is simply a collection of stars which are further away, so you don't, by eye, distinguish them, but they look like a diffuse band of light. And in an artist impression, you will have these diffuse bands and bright and not so bright points of light dominating the sky. In a modern photograph, at a dark place, you will see many stars in the sky, and also this diffuse band, which is the Milky Way, which is a collection of stars in our galaxy. So as I said, the largest amount of visible light that is produced in the universe comes from stars. In our galaxy, for example, we have about 100 billion stars. Our closest star is the sun. But there are stars which are bigger, brighter, more massive than the sun. And there are also stars which are smaller, less massive, and dimmer than the sun. But altogether, there are about 100 billion of such stars in the galaxy. And within the observable universe, there are about 100 billion galaxies. So you can imagine how many stars are there in our observable universe. So what we'll cover in this series of 4 lectures is a basic explanation of what the stars are at a very basic level, and what is their life history. That is the scope of this series of 4 lectures. We will not go into large amount of quantitative detail, but we will describe this at a qualitative level to illustrate the physics behind this as much as possible. Okay, so what are stars? Stars are self-gravitating globes of gas. What is the Earth? Earth is a self-gravitating globe of mass, which is not made of gas, but it's liquid and solids. Well, stars are made of gas, and the gas is held together by its own gravity. So gravity, by its nature, attracts every particle to every other particle. So left to itself, the gravity will tend to make the object smaller and smaller because as you bring two particles closer together, the force between them increases, and you will tend to make this a more squeezed object. And that is the tendency of gravity. So to make a stable object like the star, the gravity must be counterbalanced by something. So something must be balancing this gravitational pull so that the star can maintain its shape and size. So that comes from the pressure inside the star. So gravity is pulling it inwards, gravity is pulling the gas inwards, and the pressure of the gas is pushing it outwards. If there was no gravity, the pressure of the gas would blow the star apart. So the point at which these two forces counterbalance exactly gives you the equilibrium structure of stars. And for a star like the sun and all these bright points of light that I talked about that you see, this gas pressure mainly comes from the thermal pressure of the gas. So that is, the gas is hot, which means every gas atom or ion and electrons in there are moving about at a rapid pace given by the thermal velocity. And this gives you a pressure, and that pressure is responsible for holding the star up against gravity. So that is thermal pressure. Now, as we know, if you have something hot and you embed it in a surrounding like space, where there is very little radiation coming from outside and entering the star, so hot body is going to radiate. The radiation is going to take away the thermal energy which these particles have. These ions and electrons, as they move about, they are going to radiate at the cost of their kinetic energy. So therefore, their kinetic energy will go down, which means the temperature will go down. If the temperature goes down, then the pressure will drop. If the pressure drops, then gravity is going to pull it further together. So unless this loss of energy in radiation can be compensated by some means, holding the gas up against gravity by thermal pressure is not going to work. So what can compensate it? To compensate it, therefore, you will have to generate energy within the star. Energy is being lost from the surface in the form of radiation. You have to compensate that loss exactly. Only then can the gas retain its thermal pressure and can continue to support it against gravity. So it is essential that a star must have a source of energy inside, and this comes from nuclear fusion. Most of the stars we see are converting hydrogen into helium at the centers. And this process not only changes the element, but also produces gamma photons. A smaller fraction of stars is converting helium to carbon at the center, but the largest fraction is converting hydrogen to helium. But these processes all end up producing gamma photons. And these gamma photons then leave the site of the fusion reaction and interact with matter as they progress, heating up the matter in the process, and the photons themselves getting degraded into optical light. And the matter which has now been heated by interaction with these energetic photons will then emit its own radiation. And eventually, from the surface, you'll start getting thermal radiation at some defined temperature, which will be called the effective temperature of the star. The temperature at the center where the nuclear fusion is going on is going to be much, much higher than the temperature at the surface, where the radiation you see comes from the gamma photons which have degraded and the thermal emission that the heated gas is producing. However, the amount of energy that is being produced at the center must exactly balance the amount of energy that is being lost at the surface. Only then you have a perfect stability condition. And that's what most of these stars achieve. And even our closest star, the Sun, has hydrogen converting to helium in nuclear fusion at the center, generating energy exactly at the rate of 4 times 10 to the power of 33 ergs per second, which is the rate of loss of energy that we see from the surface in solar radiation. To study the stars further, it is useful to take a look at some of their population properties and then see in various observables where they lie. Two of the things which we can measure relatively easily in any star, at least not stars which are not terribly far away, are their brightness and their color. Now, this brightness, if we can then also measure the distance to these stars, can be converted to a measure of the actual amount of radiation leaving the surface of the star per second, which is called luminosity. So if we plot the logarithm of luminosity on the vertical axis, what is plotted here is an absolute magnitude, which is a quantity which is proportional to logarithm of luminosity. And on the horizontal axis, we plot some measure of color. So here the measure of color is taken by observing the star, measuring the intensity in two different filters. One is called a blue filter, the other is called a visible filter. So two different band of wavelengths in which you measure the intensity, take a logarithm of it, and then take a difference, which means this is a measure of the ratio of intensity in these two bands, ratio of the flux received in these two bands. So that's a measure of color. And the color changes as the surface temperature changes. For example, if you could take the full spectrum of a star, then for different stars, you will see that the spectral distribution of light, this is going from red to violet, the distribution of light will peak at different wavelengths. For example, at the bottom, the peak of intensity is clearly in the red over here. At the top, the peak of the intensity is somewhere in the blue. Our sun is somewhere here of class G, where the peak of intensity is somewhere in green here. So if we now take two bands, let's say somewhere here and somewhere there, and take a measurement of the intensity in these two bands and take a ratio, then for each of these classes of stars, we'll get a different value of ratio. So from this ratio, then we can work back and find what the temperature of the star might be. In addition to this continuum, of course, which is typically well fitted by a black hole. This is the solar continuum in red, and in yellow is a black body fit of 5,780 Kelvin. This is the Planck curve. You would have already learned about this in the radiative processes lecture. So this is a pretty good approximation to the Planck curve, but there are these other features on it. There's some excess here, there is some these absorptions here, and that comes from the atmosphere. So here you can see in the stars, you don't just have the continuum, but you also have these lines. So these are the atmosphere of the star, the atomic species there, absorbing this light at their characteristic wavelengths, and that those lines seen prominently over here. And then there is also some absorption and re-radiation that happens, which can give you a little bump somewhere else. These are small departures from the black body spectrum, but by and large, the stellar spectral distribution is a black body, and therefore we can define a temperature or the effective temperature at the surface. For the case of the sun, it is 5,780 Kelvin, and in these other cases, the temperatures will be different. And if we take the black body curve, then we can connect this B minus V, as I have noted here, which is the ratio of the intensity in these two bands, can be calibrated against temperature. So if you take the color index B minus V, then from this curve you can read off what the surface temperature is going to be. So as I said, for the sun, the color index is over here, and the surface temperature is 5,780 Kelvin. And these are a few other stars. This is a red star, Betelgeuse in Orion, and this is a blue star called Bellatrix. So that gives you a sort of range of temperatures you can see among the stars in the sky. So this color index, which is plotted on the horizontal axis, is in fact a proxy for temperature. So the temperature increasing to the left, and here the luminosity increasing to the vertically up. So in this temperature luminosity diagram, if we now plot the stars we know for which this measurement is possible. So here I have shown the result from a satellite called Hipparcos, which measured the distances of many stars and made possible construction of this diagram with a very large number of objects. And this has been further expanded now by the currently operating satellite called Gaia. But our point is adequately made from the Hipparcos satellite, so I'm going to stick to this. So this is Hipparcos data of stars in the solar neighborhood, for which accurate distances could be measured using parallax. And you can see that although a large range of temperatures are possible, a large range of luminosities are possible, most of the stars seem to fall in a narrow band in this diagram. This diagram itself, by the way, is called the Hertzsprung-Russell diagram. This is one of the key diagrams which help us study the evolution of the stars. So most of the stars we see are located in this small band over here, narrow band over here, going from the lowest temperatures to the highest temperatures uh, among the objects seen, as well as from the lowest luminosities we see to the highest luminosity we see. But it's just confined to a diagonal line. So what is the special aspect of this line? Why do most stars congregate on this line? It is not as all stars are on this line. We do see stars scattered here and there are in fact stars scattered all over this place. But there are far fewer in number. So this band of stars is called the main sequence stars. Our sun is also in the main sequence, somewhere over here. Now, it so happens that all these stars which are sitting in the main sequence are the ones which are converting hydrogen to helium at their centers. So this happens to be the longest phase of their lives. Why? Because in all the processes of fusion that you can think of, going from the lightest element, hydrogen, to the peak of the fusion curve, which is iron nucleus over here, because binding energy per nucleon keeps going up as you go up in atomic number. And then after iron, it goes down. So that means you can't have spontaneous fusion beyond this point because that will become endothermic, not exothermic. So fusion can proceed up to iron peak elements. And you will proceed in these stages from hydrogen to helium, helium to carbon, carbon to oxygen, oxygen to neon, magnesium, silicon, and then to iron peak nuclei. But as you can see, the amount of energy released per nucleon keeps going down with each step. The biggest energy available for release by fusion is when hydrogen is going to go to helium. So therefore, in the process of replenishment of energy being lost from the surface of the star, this phase where each conversion of a nucleon gives you the maximum possible energy is going to last the longest. So stars spend most of their life converting hydrogen to helium, burning hydrogen as we call it. And when that process is going on, stars will be found in this band. And since stars spend most of their lives burning hydrogen, so in a random population of stars, therefore the largest fraction will be found in this phase. And hence, most stars lie in this main sequence when we observe them. Now you would ask why hydrogen is being burned, but the center is hot. Other reactions can also go on simultaneously. It could have, in principle, if there was no very strict control on temperature. But it so happens is that there is a distinct difference in the threshold temperature at which different nuclear burning stages occur. For example, if we plot logarithm of temperature versus the energy released in the energy release rate in fusion reaction, hydrogen burning, as you can see, is mostly confined to this temperature range. The sun is over here. So with a small increase in temperature, the energy production rate will change dramatically. So as a result, to compensate for the radiation being lost from the surface, the temperature is usually kept well bounded to within a small range. And such small ranges do not admit, for example, the next stage of nuclear burning. So for the next stage of nuclear burning, then the temperature has to jump from this region to that region. And that doesn't happen while hydrogen is already burning. So in the main sequence, we can be pretty sure it is only the hydrogen fusion at the center that is powering the stars. Now, what is the temperature? The temperature at the center of the sun is about 10 million Kelvin. And that is the temperature at which this hydrogen fusion becomes possible. What is the temperature at the surface? We already discussed that. That is about 5,780 Kelvin. There is a huge difference in this temperature. So 10 million Kelvin at the center, which is required for hydrogen burning, and the surface temperature, which is at 5,780 Kelvin. So the temperature decreases dramatically from the center to the surface. So there is a small portion near the center of the star where the temperature is still high enough for fusion to occur. Most of the outer region of the star would not have high enough temperature for fusion to occur. So therefore, the fusion reaction itself is confined to a small fraction of the star. In case of the sun, it is about 10% of the total mass of the star. The rest, 90% of the total mass of the star, is not involved in fusion reaction. So no change in composition is happening in 90% of the star. Only in the central 10% of the mass is there a change in composition with time, hydrogen going to helium, because of nuclear fusion. So that being the overall qualitative description of stellar balance, both thermally and structurally. Let us be a little more quantitative now. We know that temperature decreases outwards. We know that the density will decrease outwards. Pressure will decrease outwards. Can you get a quantitative description of this? So let's then start with this picture. Let this dotted line indicate the outer boundary of the star. This is the center. And at a distance r from the center, within the star, let us consider a shell of it. And let's look at the forces on it. If the star is stable, that means all forces on this shell of material is balanced. Let's consider the thickness of the shell, an infinitesimal thickness dr. Let's take a small area A over here, capital A, and then consider this volume. Its cross-sectional area is capital A. The thickness is dr. The density at this point, at distance r from the center, is rho. The pressure at the bottom of this shell, let's call it capital P. Pressure above this shell, let's call it capital P plus D capital P. Average density here is rho, as I mentioned. So what is the force on this small piece of material? So let's first ask, what is the mass of this element of matter? Cross-section area is A, the thickness is dr. So the volume is capital A times dr. That times rho at r is the mass of this element. Gravitational force acts on this. Gravity is produced by matter which is within this shell. The amount of mass within this shell, let's call that capital M at r. So the force pulling this element of material inwards is G capital M of r A dr, the volume, times rho of r. Basically G M1 M2. And this must be balanced by an outward force, which is P times A minus P plus dP times A. P minus P plus dP times A. So we can now cancel common things from either side. P cancels, and then we can rewrite this as minus dP over dr is, I forgot 1 over r squared here. So this is M, M1 is M, M2, which is A dr rho of r divided by r squared is the force. So G M of r rho of r over r squared. There is over r squared here. And what is capital M of r? Capital M of r is integral from 0 to capital R, 0 to small r, 4 pi r squared rho of r dr. So these two together give you the equation of hydrostatic balance of the star. Mind you, this is not yet enough to solve for the structure. To solve this differential equation, we need to know one more thing, and that is the relation between pressure and density. And that will come from what kind of source of pressure is involved. If the pressure is thermal pressure, then P is rho kT over m. But then we also need to know how does the temperature change as a function of radius. We'll come to that in a short while. So in the spherically symmetric case, this is the equation we just derived in the previous slide. And we also define m of r to be this. But truly speaking, Newtonian gravity, which we have used to derive this, is an approximation. So particularly when the structure is very compact, which means when m of r values are relatively high, m over r is relatively high, then you have to add some corrections to this to account for general relativistic effects. And effectively, those corrections are relatively simple. This m gets replaced by m plus 4 pi r cubed p over c squared. And that is because pressure is kinetic energy density, proportional to kinetic energy density. And kinetic energy itself contributes to mass. All forms of energy contributes to mass. So energy over c squared will add to the mass effectively. And mass density is similarly augmented with energy density by c squared. And there is a factor which enters the denominator, has to do with the event horizon in case of a Schwarzschild metric. And instead of r squared, you now have a correction to it, r squared times 1 minus 2 gm by rc squared. Now, if this quantity 2 gm by rc square is very, very small compared to 1 through most of the stars, then we can ignore this. And if, in that regime where we can ignore this, typically we can ignore these as well. And then we are back to Newtonian gravity, which is an adequate description for stars like the Sun, as well as these large main sequence stars that we're talking about. But when you go to compact objects like white dwarfs, neutron stars, then you need to use this full general relativistic equation, which goes by the name Tolman-Oppenheimer-Volkoff equation. This expression remains the same, both in Newtonian gravity as well as general relativity. So now to solve this equation, as I mentioned, that we have to supplement this with what we call equation of state. That is a connection between the pressure and the density, the material that is inside, which is producing pressure. Once we supply that, then we can solve this set of equations and get an equilibrium structure. But before even we solve for such a thing, we can look at some of the general properties that the hydrostatic equilibrium equation puts in front of us. So let us start with this Newtonian form of hydrostatic equilibrium equation. This dpdr is minus g m of r rho of r over square. Let's multiply both sides by 4 pi r cubed and integrate over the full configuration. With small r going from 0 to capital R. Capital R is the radius of the star. Integrate the left hand side by parts, then we will get 4 pi r cubed p at capital R minus integral from 0 to capital R 4 pi r squared times 3p times dr. On the right hand side, you will have integral from 0 to capital R 4 pi r squared dr times g m of r rho of r over r. Now we can start recognizing some of these quantities. This quantity g m of r rho of r over r is the gravitational energy per unit volume at r. And then that gravitational energy density is integrated over the volume of the star going from 0 to capital R. So this means what we have in the right hand side is the total gravitational energy of the configuration, which is of course negative because the star is a bound object. So the right hand side can be simply written as Eg, where Eg is the gravitational energy of the star. Now let's look at this term. We know that pressure and the thermal energy density, or internal energy density as we call it, are related by an expression like this, where gamma is the adiabatic index or the ratio of the two specific heats. So pressure is related to the thermal energy density by gamma minus 1 UTH. So the second term here is 3 times gamma minus 1, I can take out, then 4 pi r squared dr times thermal energy density. So the thermal energy density integrated over the entire volume of the star gives you the total thermal energy of the star. So this term then is 3 times gamma minus 1 E thermal. So this was gravitational energy, excuse me, and this gives you thermal energy. This is a negative sign, I can take it to the other side. So I can then rewrite this as Eg plus 3 times gamma minus 1 times ETH is this quantity, 4 pi r cube P of r. And this, in fact, is what is known as the Virial Theorem. And it must be obeyed by all systems in hydrostatic equilibrium. Now let's take the case where the radius capital R is truly the surface of the full configuration, which means the pressure goes to 0 there. So if the pressure goes to 0 at the surface, which we define as the surface, then the right hand side goes to 0. And for thermal pressure of normal material, monoatomic gas, remember inside the material is practically ionized, so the entire star. So monoatomic consideration is fine. And in that case, the adiabatic index is 5/3. So given that, you will derive from this expression, gravitational energy Eg plus twice E thermal is equal to 0. Now remember, Eg is a negative quantity. E thermal is a positive quantity. So E thermal is negative Eg over 2. And the total energy, which is Eg plus E thermal, is therefore Eg over 2, which is a negative quantity. Because it's a bound state, the total energy must be negative, which is equal to minus E thermal. So E thermal is minus Eg over 2. Remember this, because this is a very useful expression to guide you in understanding the structure and evolution of stars. Now let's put this to some use to get some rough estimates. For example, for the sun. For the sun, the total mass is about 2 times 10 to the power of 33 grams. Its radius is 7 times 10 to the 10 centimeters. So the magnitude of the gravitational energy, which is roughly about gm squared by r, is about 4 times 10 to the power of 48 Earths. So therefore, the thermal energy must be half of this, which is about 2 times 10 to the power of 48 Earths. So this must be 3 halves capital N KT. Capital N is the total number of particles. The total number of particles could be derived from the total mass divided by the mass of the proton times what's called mean molecular weight. Mean molecular weight is actually giving you the effective number of particles in the interior. For example, if the hydrogen is fully ionized, then for each atomic mass unit, you get 2 particles. So your mu is therefore half. So m by mu mp gives you the total of particles times 3 by 2 times kT gives you the thermal energy. So you can then turn it around and ask what is the temperature that will then produce total thermal energy like this, and you will find 2 times 10 to the power of 7 Kelvin, which gives you a very good estimate of the central temperature of the sun. Mind you, although the surface temperature is only 5,780 degrees, the dominant temperature inside the star is at the center. And major contribution to pressure comes from material roughly at that temperature. And hence, you get an estimate of temperature through this process, which is closer to the central temperature. Let's put this Virial theorem to another description, a simple description of the formation of stars. So let's start with the life history of the star before this equilibrium has actually set in. Before the nuclear fusion begins, As I said, that there is no easy way to replenish the energy being lost from the surface. So the structure of such a gas cloud before this nuclear fusion begins is not fully stable. As the energy is lost from the surface, the gas cloud will keep contracting because the gravity will keep. So in the gravitational contraction of such a gas cloud, radius keeps going down, which means the gravitational energy keeps going up. Gravitational, the magnitude of the gravitational energy keeps going up. Gravitational energy keeps becoming more and more negative. Thermal energy, of course, therefore, keeps going up. Number of particles is the same, but the thermal energy keeps going up, so the temperature keeps going up. But it is not as though the release gravitational energy, which is gravitational energy became more negative, so therefore some energy was released. It is not as though all of it went into thermal energy, because the total energy is minus E thermal, which is Eg over 2, and then it keeps going down. So Eg plus E thermal is not constant. The total energy is reducing, which means it's getting more and more negative. That means for this gas cloud to keep contracting, energy must be released from the cloud to the surroundings. And exactly half the gravitational binding energy released must be radiated away. So what do we have here? So we have at a starting point a large diffuse gas cloud, which is contracting because of its own gravity. As it contracts, it releases gravitational potential energy. Half of that energy goes into further heating up the interior, and half of it is released as radiation to the surroundings. So the gas globe, upon removal of this heat, which is half of the gravitational binding energy, it contracts and heats up. So you remove heat from this gas globe, it will get hotter. So sometimes this is referred to as the negative specific heat of gravitational bound systems. But it will not only get hotter, it will also get compact. So this extra energy is coming at the cost of the gravitational energy. So it will keep contracting and it will keep getting hotter. And at some point, the interior will get hot enough for nuclear fusion to begin. And that's when the star is born. So I will stop at this point today and pick up the thread in the next lecture. Now let us see if there are questions. I saw there were some chat box questions. Let me start with those.
Sir, hello.
Yeah. So, yes, 1 by r squared was missing, as I mentioned. So how do we know the pressure is greater on the outer surface? It's not greater on the outer surface. It is actually lower. So I said P and P plus dP, and we found out that the dP is negative. So therefore, pressure goes down as we go.
Sir, am I audible?
Yeah, you are audible. Go ahead.
Sir, actually, when as the clouds or gas come together to form a star, naturally it need to try to reduce the energy level, yeah, come to an equilibrium, or reduce the energy and come to an equilibrium. But while the formation of star, it is instead trying for increasing the energy.
No, no. This is what this shows. As it contracts, the total energy goes down, keeps going down.
Okay.
The thermal energy goes up. So the total energy goes down, the thermal energy goes up.
Okay.
Because the thermal energy is only part of it. So it gets hotter, but the total energy goes down.
Is there any additional gravitational pull, not by itself, but via general relativity or something needed for the gases to come to a contraction to this much?
No, I mean, general relativity is no different from what I am describing. It's just a correction um, to the force law, and that becomes important only when it gets very compact. But the physics is no different.
Okay. Thank you, sir.
Yeah. Okay, there was another chat question which came. Why is it necessary for the loss to be compensated? What will happen if the compensation is overcompensated? If you generate too much energy by nuclear fusion, which will happen through the course of evolution at some point, then the extra pressure will expand the star, and sometimes it can explode also. So that's if you want the star to be stationary and keep its shape and size, then it need to be exactly compensated. E thermal is not negative in E total. E thermal is positive. E gravitational is negative. The total energy is negative. Yes, why the half the gravitational energy should be radiated away? As I mentioned, this follows from the Virial theorem and Virial theorem follows from the hydrostatic equilibrium that unless half the energy goes away, the contraction can only proceed as much as will correspond to twice the amount of energy going. So if you take a little energy away, then contraction will proceed as far as the gravitational binding energy to drop by twice the amount that will be. If you don't take away any energy, the cloud will not collapse. Okay, let me see if there are questions in the other place. I have there is nothing here. How does a gas cloud have a gravitational pull? Everybody has a gravitational. So even in your body, every molecule attracts every other molecule by gravitation, except in this scale, other forces are more dominant. But gravity is always present. Okay, I have not discussed Jean's mass, so I will not answer this question in detail. Whether a gas remains molecular gas or not depends on the temperature. It depends on what temperature it will achieve. Once it starts getting hotter, first the molecules will dissociate and become atoms, and then as it keeps getting hotter, the atoms will be ionized and so on and so forth. So it depends on the mass you start with. If you start with a very small mass, it will never get hot enough, and van der Waals forces can stop the collapse, in which case molecules may remain molecules and you will get planets. Or if it is somewhat higher mass, then molecular gas will split into atoms, and then you can get an atomic structure, and you can get brown dwarfs. If you have more massive, then everything will get ionized, and you will get a nuclear fusion and you get stars. It just depends on the starting mass. Yeah, because in this, how did the second term come on the LHS? I integrated the second LHS by parts. So multiply by 4 pi r cubed and integrate by parts. The integration by parts will always give you two terms. The second term comes from this integration by parts. Why is gravitational energy decreasing? As I said, the gravitational energy decreases on contraction. So if an object contracts, then the gravitational energy will decrease, which means its magnitude will increase with a negative sign, because the gravitational energy is negative, right? It's a bound object. It is minus g m squared over r. So as r goes down, g m squared over r value will go up, and since the overall term is negative, it will keep decreasing. Why is the pressure zero? The surface of an object is defined by zero pressure. If the pressure was not zero, then there will be movement at the surface, right? Because outside is vacuum. So if the pressure is not zero, then material will start moving due to that pressure. Okay, what will happen when hydrogen converted to helium? We will come to that in our discussion of stellar evolution. I will not I'll discuss this today. This is going to be part of our 4 lectures. We will be talking about formation of heavier elements briefly. Up to iron certainly, and beyond that, I will be talking about towards the end of my lecture in a brief fashion. All right, it's past 11 o'clock. We'll close this today, and then we will pick up tomorrow at this point. Thank you. We'll leave this now and start tomorrow.